Okay. Welcome back, everyone. We're talking about Chapter 6, the real numbers and their representations, in Math 101. Last time we saw this slide about real numbers and similar types of definitions. Natural numbers, again, are the counting numbers, the set 1, 2, 3, 4, etc. Whole numbers are the set of natural numbers plus 0. Integers are the same thing, except you start going negative. Rational numbers is a quotient, and we're going to talk about what a quotient is later, but basically it's a fraction where you have a numerator over the denominator. It's a ratio of two integers, hence the term rational, with the denominator not equal to 0. Irrational numbers are numbers that are on the number line that are not rational. We're going to talk about that in a minute. And real numbers are those numbers that can be represented by a point on the number line. Some examples for irrational numbers are listed here. We talked about pi last time, the ratio of the circumference of a circle to its diameter, and irrational numbers that do not either repeat or terminate by virtue of their calculation. So these little check marks here in front of the 3 and 7 on this slide refer to the square root. Is the top of the check mark really should go over the number, but it's very hard to do that with the font that I used. And real numbers are numbers able to be written as a decimal. So the real numbers also include rational numbers that end or repeat digits. So they have terminal digits, so like in the example of 1 over 3, that's 0.33333, and so on. And 3 over 11 is repeating decimals, where you have the same combination of numbers that repeat. In real numbers, you also have greater than or less than symbols, and we have used these as an analogy last time when we're talking about subsets and proper subsets. The small end always points to the smaller number, so 3 is less than 4, 7 is less than 12. The symbol greater than or equal to has a bar under it. The bar indicates equal to, and less than or equal to is the arrow pointing to the left, and an equal sign underneath. If either part is true, then the inequality is true. So if we're talking about inequalities in numbers, in real numbers, or any types of numbers, we're talking about inequalities, and we're asked to find out whether or not the statement is true. Be very careful that either part of the statement, the mathematical statement, less than or equal to, or greater than or equal to, if either part of that is true, then the inequality is true. And we're talking about additive inverses. Numbers are added to the opposite, summing to 0. So if you're looking at the number line, a number such as the number 3, negative 3, and its additive inverse 3, if you add those together, you would get 0. So a number that added to its negative, the negative is the additive inverse, or in the case of a negative number, the positive number. The key here is that the distance from 0 on the number line is the same in both directions. Double negatives. The book has some good examples about this. A double negative is a positive. So if you have a number x, the negative of its negative is a positive. So if you have a 4, for example, the negative of 4, or negative 4, the negative of the negative would be positive 4. Check the book for some examples on that. When we're talking about absolute value, similar to additive inverses, another way to say is that a number and its additive inverse have the same absolute value. That is, the distance between 0 and the number on the number line. Now, absolute value is written with these vertical bars around the number. So the vertical bar next to x, the absolute value of x, is x if x is a positive number, that is, if x is greater than or equal to 0. And the absolute value of x is x if x is less than 0. So once again, if you take the absolute value of 3, that is 3. But the absolute value of -3 is 3. So think about it in terms of almost like it converts a negative number into a positive number. So you're looking at basically how far away the number is from 0 on the number line. So the result of adding two numbers is called a sum. Now, if you have the same signs, that is positive signs, add them together and use the sign they came with. If you have two numbers that you're adding together and you're adding them, and one of them is negative, one way to do this is to subtract the smaller absolute value from the larger to find the absolute value of the sum. The sum is positive if the positive number has the larger absolute value, and negative if the negative value has the larger absolute value. I'm going to try and switch screens here, so please bear with me as we go forward with this. Okay, hopefully this is recording, but if we are talking about, just real quickly, if we talk about absolute value here, if we have a number 3, the absolute value is 3. If you have a number -3, that's an absolute value, this is also 3. Okay. Now, we were talking about adding and subtracting. So if you have a number, let's say 3 plus 5, you add the absolute values of those and you get a result. Okay. This is the sum. If you have a negative value, 3 plus 5 is this, or 3 minus 5 is the same as saying 3 plus -5. So if you're adding a negative value to this. You consider their absolute values, 3 and 5. That's a absolute value sign. And you subtract the smaller number from the larger number. So 5 minus 3 is 2. That's the absolute value of the response, of the sum, if you will, and it accepts the symbol from the sign, that is, from the larger number. So our response here, 3 plus -5 is -2. Another way to look at it is on the number line. If you have 0, 1, 2, 3, and -1, -2, -3 on this side. And let's say you started with your 3 here, and you said, okay, I'm going to add -5. It's the same as taking away 5. So 1, 2, 3, 4, 5 gives us a value of -2. Now, again, please bear with me as I go back to the other screen. Okay. Okay. Subtraction, the result of subtraction is called the difference. So if you have a number a and b, a minus b is the same as a plus minus b. So there's a relationship between addition and subtraction here. An example is just like the one that I had done a moment ago with addition, the addition of unlike signs. With multiplication, the result of multiplication is called the product. To multiply real numbers, if they have like signs, you multiply the absolute values to find the absolute value of the product. The product is positive. So if it's positive times a positive, the result is positive. It's negative times a negative, the result is positive. But if the signs are unlike, that is, one's positive and one's negative, you multiply them together, and the product is always going to be negative. So for instance, on this screen here, we multiply signs. We have positive times positive is positive, negative times negative is positive, and then anytime there is a single negative in there, it's always going to be negative. So 3 times 2 is 6, negative 3 times negative 2 is also 6, but 3 times negative 2 is negative 6, and negative 3 times 2 is also negative 6. Dividing is the result of a division problem is called the quotient. When you divide real numbers, again, with like signs, you divide them with the same sign by dividing the absolute values to find the absolute value of the quotient. The quotient is positive. So if they're both positive, the result is positive. If they're both negative, the result is positive. However, if they're unlike, just like in multiplication, you divide them and the quotient is negative. One little pointer here is that division by 0 is undefined. In other words, you cannot have a division by 0. If you try it on your calculator, it will give you an error message. Reference the examples in the book for some of the multiplication and division. But if you turn to page 238, we will look at some of the exercises there for examples. So if you look at number 19, page 238, you have negative 12 times negative 2. Now, a negative times a negative is going to be positive, so we take the absolute values. 12 times 2 is 24, and a negative times a negative is always going to give us a positive. Similarly, in number 25, we have a division problem. 36 divided by negative 6. 36 divided by 6 is 6. But since you are dividing a positive by a negative, our result is also going to be negative. So, moving right along. When a problem involves more than one operation, there is something called the order of operations. The order of operations is as follows. The first step is, if you have a fraction bar, you work the problem separately above and below the fraction bar. So, for example, if you have a problem that performs this, then you can do the numerator and denominator separately. The next step is to use 3 to 5, rules 3 to 5 within each set of parentheses or square brackets. So you look at the brackets, the innermost set, and you work your way outward. We're going to go through all of the steps, and then we're going to do some examples. This third step is to apply any exponents that there are. In other words, are there squares or cubes that that numbers have to be multiplied against? Do any multiplications or divisions in the order that they occur in, working from left to right, and do any additions or subtractions in the order in which they occur, also working from left to right. A little acronym is PEMDAS, please excuse my dear Aunt Sally, where P is parentheses, E is exponents, M is multiply, D is divide, A is addition, and S is Sally. Okay, let's do a couple of examples here in the order of operations. So if you look in section 6.2 on page 239, we have a problem number, let's do problem number 34. In number 34, the problem is -10 plus 4 times, that dot means times, -3, all of this divided by -7 minus 2. So what we want to do here is we want to do the numerator separately. So you perform the PEMDAS, okay. Please excuse my dear Aunt Sally. So we're looking at parentheses, exponents, multiplication, division, addition, and then subtraction. So we're looking at parentheses. So -10 plus 4 is -6 times -3. So that's the numerator, -6 times -3, which gives us +18. The denominator is -7 minus 2, or -9. Now the numerator is positive because a negative times a negative is a positive, but the denominator is negative. So the result is going to be negative. This is an example of the order of operations. If you look at number 35, you have -8 times -2 minus 4 squared plus 7 minus 3. So once again, we look at the parentheses first. So 7 minus 3, we'll look at the brackets here. So inside this parentheses, 4 squared is 16, plus 7 minus 3 is 4. Okay, and then -8 times -2 is +16. So this negative sign comes right down. So 16, we still have numbers in parentheses here. So 16 minus 16 plus 4, which is 20, equals negative 4. So the solution to this is negative 4. And there are a number of other examples, exercises in the textbook as well for the order of operations. Now, there are some other properties in addition and multiplication. These properties are called the closure properties. A plus B and A times B are real numbers. So if you see a number next to another number or a letter next to a number, that indicates that they're being multiplied. The commutative properties are allowing them to flip around. So A plus B is the same as or equals B plus A. So 3 plus 5 equals 5 plus 3. Same thing with multiplication. 3 times 5 equals 5 times 3. Associative properties are listed here as well. If you have a quantity A times B in parentheses, and that's multiplied by C, that's the same as saying A times the quantity B times C. Similarly, in addition, a quantity A plus B plus C is the same as a quantity B plus C plus A. And then lastly, on some other identity definitions, if you have there is a real number 0 that exists such that if you add that number to any number, you get the original number. So A plus 0 equals A. Common sense, you don't add anything to A, you get A right back. Similarly, there's a real number 1 such that if you multiply any number A times that, you would get the number A. A times 1 is A, and 1 times A is A. There's an inverse property as well. For each real number A, there's a single real number negative A, so that if you add them together, here's your inverse, additive inverses again. A plus negative A is 0, and negative A plus A is 0. And for every non-zero real number, A, there's a single real number, 1 divided by A, such that A times 1 over A equals 1, and 1 over A times A equals 1. An example of this is here. So for instance, if you wanted to say A is a number, and you had another number, this is a multiplied, 1 over A equals 1. So if A were, say, 3 times 1 over 3 equals 1. Okay, that makes sense. You have 3 thirds, an item that is 1/3 of something. You have 3 of them, it equals 1. So for instance, if you had a pie, and this pie is divided into 3 parts, and you have all 3 of them together, you get one whole pie. This is an example of an inverse property. Distributive properties, if you have a number inside parentheses that's a sum, A times quantity B plus C, you take the A and you multiply it by each one individually. So an example of the distributive property here would be if you had, let's say, 3 times 5 plus 7. This is the same as saying 3 times 5 plus 3 times 7. This is especially useful when we get into algebra because sometimes you may wind up having a letter A and you have to use this distributive property across these, and you might get 5 times A plus AB, for instance. It's especially useful in that avenue. So remember the definition of rational numbers. We have a decimal representation of rational numbers. A rational number is a quotient x, where x is a quotient of two integers with a denominator not equal to 0. And rational numbers are in their lowest terms when they follow the fundamental property of rational numbers. If a, b, and k are integers with b not equal to 0 and k not equal to 0, then any number, any ratio would have the response here. You have a times k divided by b times k. It equals a over b. The reason for that is because if the k over itself, any number divided by itself, is going to be 1. Okay, 6 divided by 6 is 1. 12 divided by 12 is 1. K divided by k is 1. So even if you don't know what the number is, any number divided by itself is going to be 1. So let's look at some exercises in the textbook for section 6.3. It gives you multiple choice options. There are some expressions that are equivalent to the given rational number. This rational number 4 over 8. This rational number has the same representation as A, which is 1/2, C, which is 0.5, and D, which is 0.50 with a bar over it. When the number has a bar over it, that means that that's a repeating number. So 0 is one of those special cases that if you have a bar over it, it's the same as not being there at all. Number 2, 2 over 3, is the same as B, which is 0.6 bar, which is 0.66666. If you plug 2 over 3 into your calculator, that's what you'll get. The same thing as 20 over 30, which is the same as saying 2 over 3 times 10 over 10. And also decimal representation 0.666 dot dot dot. Well, remember that dot 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 is an ellipsis and it goes on forever. And some other examples are there as well. If you have rational numbers, A divided by B and C divided by D, remember the denominator cannot be 0. A divided by B equals C divided by D if and only if A times D equals B times C. So let's look at this momentarily here. If we have a number let's say you have a number 3 divided by 5 equals A over 20. Okay. Let's say that you want to try and figure out what A is. In order for these two fractions to be equal, you can perform a cross product here. 3 times 20 is 60 equals 5 times A. And here's a little algebra being thrown in here. In order to solve for A, divide both sides by 5. Because you can do the same thing to both sides. It doesn't change the equation. The 5's cancel out, and you're left with A equals 12. So back in the original equation, 3 divided by 5 equals 12 over 20. So the solution here is A, and that's because of this the cross product. We did a cross product. The only way that they could be equal is if 3 times 20, which is 60, divided by 5, or 60, equaled 5 times this numerator A. So that example is an instance of the cross product test. For rational numbers, if you have A divided by B and C divided by D being rational numbers, then you can add fractions together by using these formulas. You can add and subtract fractions together. And this is in section 6.3. And there are some good examples in the textbook in this section. So let's look at some exercises here. Exercise number 19 in this section. Perform the indicated operations and express answers in lowest terms. Use the order of operations as necessary. So in number 19, we have 3/8 plus 1/8. Now, when you're adding fractions like this, if the denominators are the same, that is, the number on the bottom is the same, the result is that the denominator stays the same and the numerators just get added. So this would be 4 over 8. And 4 over 8 is the same as 1 over 2 times 4 over 4. And we know that any number divided by itself is 1. So a half times 1 is the same as 1/2. So the answer here to this problem is 1/2. Same thing with number 20. If we look at number 20, 7 over 9 plus 1 over 9 is 8 over 9. So those are pretty easy to do when you have fractions that have the same denominator. You can add and subtract them quite easily. But when you start having some challenges are when your denominators are different. You're performing a mathematical function. So if we look at number 23, 2/3 minus 7/8. 2/3 minus 7/8. So if we use the formula that's listed on page 244, the formula is if you have A divided by B minus C divided by D, that's the same as A times D minus B times C, all divided by B times D. So A, B, C, D. So 2 times 8 is 16 minus 3 times 7. There's that kind of that cross product thing, 3 times 7, 21 divided by 3 times 8, which is 24. So 16 minus 21 is -5 over 24. So even though this seems like a clumsy fraction, this is the solution to this problem, -5 over 24. This is one way to do this. Another way would be to say, okay, usually we use something called the lowest common denominator. If we look at the 3 and the 8, we can say, well, the lowest common denominator for these is 24. In other words, 3 times 8 is 24, and 8 times 3 is 24. Well, how can we make this number on the bottom into a 24? Well, we can multiply it by 8. But we also have to multiply the top by 8 so that we're not fundamentally changing this part of the equation. Similarly, over here, we can convert this into 24 on the bottom, but you have to multiply top and bottom by this number. Any number divided by itself is 1. So you're not fundamentally changing the equation, but what you've done here is you're saying, okay, 16 24ths minus 21 24ths. And it's essentially the same equation that we got up here, and we will come up with the same result, -5 24ths. If you multiply rational numbers, you have ratio of numbers. Look at how these are spelled out. A numerator over denominator, A over B times C over D equals, you multiply the numerators together and you multiply the denominators together. It's fairly straightforward. The examples in the book are what I'd like you to look at for this one. So number 27, for instance, 3 over 4 times 9 over 5. You multiply the numerators together. 3 times 9 is 27. And 4 times 5 is 20. So it will be 27 20ths would be the response on that one. And the same rules apply for negative numbers. So if you had 29, for instance, negative 2/3 times negative 5/8, the negative 2 times the negative 5 is multiplied together, and you get positive 10 divided by 3 times 8, which is 24. So 10 over 24, that's the same as saying 5 over 12 times 2 over 2, remembering any number divided by itself is 1. So the 1 is can kind of be canceled out. So what you're left with is 5 12ths. In division, if you have real numbers, a divided by b, a times 1 over b is the same as saying a over b. And if you have rational numbers where a and b and c and d are dividing one another, it's the same as taking the inverse and multiplying. So here's some examples. 31. So number 31, 34, and 36. So number 31 on page 252. So 5 over 12 divided by 15 over 4. This is the same as you take the second number, the number that's after the dividing symbol, and you flip it. You invert it, and you multiply. So what you're left with here is 5 over 12 times 4 over 15. This is the rule that we're talking about. Now, we just multiply them through. So 5 times 4 is 20. So the numerator is 5 times 4 is 20. And the denominator is 12 times 15, which is 180. So 180 and 20, just by looking at those, you can see that those are divisible by 20, actually. So 1 over 9 times 20 over 20. Any number divided by itself is 1, so our solution is 1 over 9. Number 34, negative 3/8 divided by 5 over 4 is the same as saying negative 3/8 times 4 over 5, or negative 12 over 40. Both of these, again, are divisible by a common number, which would be 4. So negative 3 times 4 over 10 times 4. That's where negative 12 over 40 comes from. Any number divided by itself is 1. So these cancel out, and you're left with negative 3/10. Okay, then we have to use some of the other properties, the order of operations here in number 36. 2/5 divided by -4/5 divided by 3/10. So first we do the parentheses, so -4/5 times 10/3 gives us, and again we have 2/5 divided by this. So 2/5 divided by -4 times 10 is -40. 5 times 3 is 15. So now we have 2/5 divided by this. This is the same as saying 2/5 times 15 times the inverse, 15/-40. Okay, so we can multiply this through. 2 times 15 is 30. 5 times -40 is -200. Both of these are divisible by 10, so we're getting 3/-20. And then, again, if you have 3/-20, that's a negative number. That's the same, so 3/-20 is the same as -3/20, and it's the same as -3/20. They're all the same. When we start talking about an average, the arithmetic mean is the average. The way you take an average is by summing up all of the numbers that you're looking at and dividing by the number of how many that there are. So if you wanted to average these numbers, 3, 4, or 2, 4, and 6, you would add those together and divide by how many there are to get the average. We talked earlier about terminating decimals and repeating decimals with rational numbers. We've also talked about the quotients of integers being rational numbers. And we've provided some examples, but the book has some additional examples. Please take the time to review the book and email me if you have any questions. Thanks very much for your time, and I will see you next Tuesday.